Professor Malakar is an assistant professor in the Department of Computer Science and Engineering at IIT Kanpur. She received her PhD from Indian Institute of Science, Bengaluru, and did her postdoctoral research at the Argonne National Laboratory in USA with some of the most powerful top supercomputers in the world. Her research interests are in parallel communication optimization, in situ analysis of large-scale simulation, and topology-aware data movement and high-performance I/O. So Professor Malakar has been working at the cutting edge of some of the most illustrious projects all over in the entire globe regarding high-performance computing and their application to science problems. And these are very high-profile projects which our entire world is looking at. It is our pleasure to listen to Professor Malakar. So Professor Malakar, you are very much welcome, and over to you. You may please.
Yeah, thank you to the organizers for inviting me. This 1 hour I have prepared a few slides to help you understand programming using MPI. And the first question is, why are we looking, what is MPI and why are we looking at MPI? So before we start off, I wanted to show you the current state of the art of the performance of supercomputers across the world. So if you look at the brown triangles in this graph, this shows the performance of the topmost supercomputer from around 1993 to when this list was actually started. This is the list from top500.org. It's a website to all the way till today. And
so, Professor Malakar, can I interrupt you for a moment?
Sure.
Just for some admin. So I am muting everybody. Then Professor Malakar, you have to unmute yourself once. I am muting everybody so that
Sure,
there is no. Okay, you may please unmute yourself. Yeah, Professor Malakar, you can unmute yourself.
Yes. So, so you can see the y-axis is log scale, and you can see the performance has been exponentially increasing. The compute capacity of the topmost supercomputer, as well as you can also see the number, the last entry, the number 500 in the list, and this changes over the years. This has changed across countries, vendors, and so on, architectures, and so on. Right. So this is what it looks from outside. This is a picture from IIT Kanpur's supercomputer, Param Shakti. And if you look at the list of supercomputers, and I just wanted to give you an idea of what is the number of computing cores that are present in this massive systems, right? So 7 million cores, 2 million cores, and so on. So they have huge capacity, and why you already know why, right? So we have big science problems which require such capacity, and one of the major programming paradigms that is used to program these massive supercomputers is using MPI. So you have already seen OpenMP, shared memory programming. So there the concept is that you have a single system and you can spawn a number of threads on all the cores of that system. It can be OpenMP threads, it can be P threads also. And today what we are going to look at is MPI. So this is a standard for another kind of programming model which uses message passing in a distributed memory environment. Like you saw, the supercomputing list started from 1993. This message MPI interface efforts to build such a standard which can be used across the world, by different teams. It started in 1991, the MPI forum was formed, and they kind of look at the different versions. So this year the version 4 was released, so every year they add new capabilities, like the architecture evolves, the software also has to evolve at a certain rate. So if you think of a simplified model that MPI works on, this is kind of a distributed memory model where you have different systems. So these are the 4 different systems, and in each of these systems, so today we have multi-core, so you can spawn multiple processes on each of these systems. The number of processes you can spawn, it's certain noise. I can hear a certain noise. Is everyone able to hear me? Okay, this is better. So the total processes that the number is limited really by the operating system, but for performance, if you want to get good performance out of all the cores that are present, it's really you should be spawning maximum to the number of virtual cores that are present in the system. Okay. So this is slightly different from OpenMP. OpenMP is used for shared memory programming, where you have one system. Here you can spawn multiple processes on a single system as well as across all these systems. So the memory layout, when you look at all these processes, I will not go into much depth, but this is something that you may want to keep in mind, that every process has its own address space. Okay, there's a certain format in which it's laid out in memory, and so nobody can read or write into other processes' memory unless and until you actually give explicit permission. Okay. So starting with what is MPI and how do you actually program using this model, this standard, right? So a simple case, you have 2 processes. If you want to send some data, so remember we are working on a very large system, so there is hundreds of you can think of computers, right? So 100 of nodes, we call them compute nodes, are connected. And once you're done with the computation part, you need to communicate. So for example, there are 2 processes here. Let's say they may be on the single system or a different system, and you need to communicate. So how do you do that? You basically send a message. Okay, so that's what I'm going to cover. That how do you actually...
Professor Malakar, I think we have lost the slides. Can you share once again?
Oh, okay. Okay. So
it is back.
So let me just start from this slide. So basically, we are the basic primitive of this whole message passing model is send and receive. So one process basically sends a message to the other process, and the other process receives. Okay. Like I said, there's one distinction because we're dealing with process and not threads. So we should always remember that whatever variables you declare in a process, these are all local variables. If you want to change the value of, I'll show you example programs. So if you want to change a value in one process, you can do so, but it will not be reflected in the other process. So these variables are local to every process. So if you do the computation using this code, this is the output. You can also have same value, and you can have different statements. So it depends on how the programmer wants to code. So here we have the same variables initialized to the same values, but the computation statement is different, right? And so hence the output is different. So what kind of program we want to write, it depends on our application, right? But one thing to remember is we deal with hundreds of processes. We don't write 100 different codes. Typically it's a SIMD program and we write single code. It operates on different data. This is the most simplistic model. So let's think about this simplistic model for this lecture. Okay, so just to again, help you understand better. So in sequential code, right, you must have written some sequential code in C, maybe. So you get one executable, right? So here also you get one executable. It doesn't. So one executable per system. Okay, so what happens is internally there are a few other steps, but to state it simply, so you compile in very similar way, and I'll show you the example. And the executable, it's basically transferred to all the systems that you're running on. Okay, and whatever number of processes you would have in that system, that many number of executables, processes you will be actually running on that system. So let's look at another example. So it's possible that there are multiple processes sending data at the same time to different processes. So basically the source here in this example was process 0 and process 2. These were the two sources, and the destinations were process 1 and process 3. Okay, if this is your intention, your code also has to reflect that, right? So we will try to look at some examples. So finally, getting started, right? So before we write longish code, we'll start with just a simple line, the basic simple code that we always start with, hello world, right? And if you're using MPI, you will have just these two statement. There's an initialization part. As you can understand, we are trying to run a program not on one core, but on hundreds and thousands of cores, right? So I showed you the supercomputers have millions of cores, and there are applications that do run on millions of cores, right? So the initialization basically takes care of a lot of internal state of helping preparing for the communication. So like I showed you an example, two processes are sending data to two other processes. So imagine 100 processes sending data to another set of 100 processes, right? So it needs to. So how does this work, right? So there has to be some bookkeeping, right? So all these things are taken care of by the MPI library. We don't need to worry much. So I'll show you examples. If we just write these 3 lines and I run this code, I'll show you how to run. So if I run this code, let's say I tell MPI that I want to run this code on 10 processes. What it will do is it will run this code on 10 processes on the 10 systems or 10 cores that I have specified. It will print 10 hello worlds. Okay. So another few basic things, right? This is necessary for all kinds of MPI programs that you may write. There are 2 functions which help you get the total number of processes. So when I run, I do specify, but if the programmer from the program, right, if you want to know that how many processes is this particular code running on, and you can run really on any number of cores. It's a runtime decision. So that number is, for that you have to query using this function MPI size, and another function called MPI rank, which gives you an identity. So every process is basically ranked. Every process has an identity. Starting from 0, it gets a rank. It's an MPI rank. This is different from operating system. It's an MPI rank. Okay, so how to compile a simple code? So if you install any MPI, you will get a compiler, something like MPI CC. So for the simple impitch with GCC, you will get MPI CC as the compiler name, and this is how you compile and this is how you execute, right? So that 3-line or the 5-line code, the last 2 codes that I showed you, these are the only 2 simple steps that you need to do. That the only difference is you may have used GCC. Instead of that, you use MPI CC because it has to link all the MPI libraries and the header files. So that is taken care of by MPI CC. And then you use MPI run just to execute the code. So MPI run basically takes care of spawning all the processes on all the cores and nodes and everything. If you want to run on 6 core, you will just say -np6, which means I want to run on 6. If you run on different hosts, that's also possible. Let's say you are in a shared cluster in your institute. You have some cluster in your lab, and that cluster may be shared. And you have figured out that host 3 is busy. So you want to give more computation to host 1. So you can specify that, okay, host 1, you want to run 3 processes and so on. And it will run 3 processes on host 1, 2 on host 2, and 1 on host 3, and so on. So this is some example. Of course, if you're running on supercomputers, you typically have a altogether different way of running programs, which I'm not covering in this lecture. Okay, so just to recap, so if you give this command MPI exec, so MPI exec is similar to MPI run. It's exactly the same executable. And you say MPI -np8 -f host file. This is the host file. I say 2 processes on each node, every system. So MPI will spawn 2 processes on every system, and this is the ranks. By default, it will start from the first system that you have. So 0, 1 rank, MPI ranks are placed on the first system, and so on. So how this happens is, so I'm not going to very much detail, but very simply stated, there are some proxy executables that take care of these spawnings, and this is a code that is I've taken from the MPI source code. So we'll move on to more programming. So like I said, we assume that the same code, basically same instructions are running on all these processes that you have spawned. Now you know how to spawn processes. You just have to say MPI run -np8, and you have all this process. And there is maybe somehow there is data distributed. Okay, there are a number of ways to do that, to distribute data across all these processes. But let's say we have some data distributed and you want to do some computation, right? So how do you do that? So for that, we need to know some MPI functions. So let's start with that. And this is something that we will come once we know how to write MPI code. We will probably try to think of how to write a parallel sum of numbers, right? You already know the serial sum of numbers, and this is an algorithm for parallel sum of numbers. But how to write this in MPI, we will see this after we learn a few primitives. Okay. So to install mpitch, it's simple. In Ubuntu, you can just do sudo apt-get install mpitch. That's all. This is an MPI library. Mpitch is the name of MPI library. So coming back to our code, right? We showed 4 important functions: MPI init, MPI comsize, MPI comrank, MPI finalize. Other than MPI init and finalize, every other MPI function has one necessary argument, which is the communicator. Here, MPI comword is called the communicator. It's a global communicator. What does it mean? It has info. So any query you want to do about any process, any MPI function you want to write, you have to use MPI comword in that. It has information about all the ranks that are globally present. So 0 to n num tasks minus 1. Okay, because the ranking starts from 0 and num tasks is the total number of tasks that you have. So 0 to num tasks minus 1 are the IDs of the processes. So it basically defines the scope. It contains information about how to basically do the communication from. You can also divide the communicators, so then you will have sub communicators and so on, but we are not covering that here. So let's move forward to understanding how do we actually do message passing, what are the function calls. So like I have already covered, so here is in this global communicator, so it has information about all the processes ranked starting from 0. Okay. So another important argument that is present in almost every MPI function is the data, right? So MPI message, it has a data and it has like an envelope. The envelope contains the origin of the message, like who has sent the message, who is the receiver of the message, the communicator, and the tag. Okay. And this is typically used in all the MPI point-to-point communications, which I'm going to cover next. Basically, there are two different types of communications. The one on the left is called point-to-point. The one on the right is collective. What's the difference? In point-to-point, one source sends message to one destination. In collective, there can be one source can send message to multiple destinations. One process can receive message from multiple sources and so on. Okay. We'll try to look at both very quickly, but starting with point-to-point communication, right? So two important functions for point-to-point communication. So if you want to send data from one process to another, so we'll call the sender, the process who is sending, sender. It has a message, which I've shown in this light colored box, and it wants to send a message to the receiver. So basically, that message is nothing but some data. Right? That data has to be communicated over the network, maybe, to the receiver. Right? So this is what the function prototype looks like of MPI send and receive. You will see there are few things that are common, which is the address of the data, right? Buffer, that is the address of the data. Now remember, let's say these are two different processes, okay, on different systems. So the memory is completely disjoint, right? This buffer, even though I've used the same name here, it actually points to two different memory locations. So buff in sender, buff points to the data location where the sender wants to send the data from. And in the receiver, it points to some location where the receiver wants to receive its data. Okay, so they will declare, of course, you can use the same statement to declare buff. You can use the same variable, but actually they are distinct, process address spaces. Right? Second is count. This count should ideally match. If I am sending you, 10 bytes, you should be receiving 10 bytes. You should not say that I only want to receive 5 bytes, right? So you have to at least receive 10 bytes, otherwise there will be problems. MPI data type. There are, as you know, there are different data types in float, and the sizes of the data types vary. Because here we are dealing with two different processes. They don't know what is the sender going to send. So that information has to be somehow encoded, right, in this function calls itself, right? So that's why we have this buff, count, data type, and then destination and source. Who are you sending to? You have to tell MPI library that please send this message to process number so and so. Okay. There's a tag which basically matches that, okay, this particular message is indeed intended for this particular receiver. And then there is finally communicator. Like I said, communicator has to be present in all the calls. The status you can ignore for a while. This is blocking send and receive. When, simply stated, when a process calls MPI send, it's going to block until the receiver has actually received the message. So data type, there are like multiple data types. These are some some data types defined in MPI, but you can also define newer data types. You can construct new data types from the basic data types. Okay, so let's look at example with MPI send receive. So here I'm sending a simple message, hello there. Okay, I have two processes. I will call the 0th process, the rank 0 process as sender process. It's sending data to receiver process whose rank is 1. Now note the tag, which is the last but one argument in the send process, is so 99. This is the tag that matches with the receiver process. It also has 99. In the receiver, I have said that I want to send MPI card. That's the data type. So data type also matches. And in the receiver, I have said I'm going to receive 20 MPI cards. 20 MPI cards. It's not 20 bytes, but since MPI card is size is byte, so here it's 20 bytes. And in the sender, it tells that, okay, the size of this message is whatever, hello there. It's less than 20, but receiver has to have at least the size of that message. So it has 20, it's fine. So this program will run fine. Okay. So I'm not showing the init and finalize. You of course have to have the init and finalize before and after this code. Other than that, this code will work fine. Okay. So when the receiver will print received, it will be printing hello there. That is all the output will be from this code. Okay. So I had a status argument at the very end. That status argument is actually very useful. It can be you can query the status argument to get the actual count of the message length. The third bullet point here, that is actually very useful. So you get the actual count, how much data did you actually receive from the sender. It's possible that sender, I mean, of course it's just a programming error, so maybe you have missed out sending the entire data. You may have specified a shorter number of bytes, and this is one way to, sometimes we used to debug that, okay, I thought that I have sent 20 bytes, but it shows me that the receiver has only got 10 bytes. Okay, so one thing, if you are going to program in MPI very often from now, let's say in future, one thing to remember is parallel programming is debugging is quite challenging. Okay, because here, like you can see, we have to explicitly say a lot of information. We have to, as a programmer, it's the responsibility of the programmer to make sure that I have specified everything correctly. I have the same data type, it matches, the count matches, and so on, right? So another interesting wildcard receiver and tag the receiver can use as for source and tag is MPI any source, MPI any tag. So what happens is, if let's say you were expecting data from 100 different processes and you don't know what is the order in which you will receive. So remember I said that this is a blocking call. The receiver doesn't want to block for all the processes. Let's say the receiver is the last rank, the 99th rank. So it doesn't want to block itself for all the processes 0, 1, 2, 3, because anyone can send in any order. It's network, the order can change. So this is a very nice wildcard that they have, MPI any source. So you can receive from any source. Again, you can query the status argument and you can know which source actually you've got the data from. Okay. So when we say blocking, not only does the function, the process blocks, It's also the case that you cannot use that buffer until this, the call has gone through, the receiver has received. So sometimes MPI implementations, they do an enhancement for performance, which is message buffering. So MPI buffers on your behalf, and the process can go on, although it is called blocking, but this is just a performance improvement that sometimes may be implemented by the MPI implementations. In fact, most of them do implement, because you don't want to unnecessarily block the sender just because the receiver is not yet ready, right? So remember, these two processes are on different systems. So like for example, I'm sending something to some person and I don't want to wait till that person has received that packet, right? So so the message buffering is typically used. Another thing that you may want to keep in mind is this is implementation dependent. So how they implement and so on is not what you should write your code on. You should still write a code that will be deadlock free. And why am I talking of deadlock? I'll show you one quick example here in the slide. So here, process 0 is saying MPI send, process 1 is saying MPI receives. So this is the program order from top to bottom. So process 0 has 2 MPI sends and process 1 has 2 MPI receives, right? So this code will work fine, right? Whether MPI has done message buffering or not, it doesn't matter. This code will work fine. So we will call this code as safe code. On the other hand, if process 0 also calls MPI send and process 1 also calls MPI send, there will be a deadlock. If you forget about the message buffering, this is a blocking call. Both are waiting for the other process to receive, right? So this is what is called an unsafe code. Although MPI implementations will, for small messages, this code will work fine and you will think my code is great, but actually there's an error in your code which will not work fine when your message size is very big. Okay, so that's why we should never write unsafe code. We should always write safe code. No matter MPI implementation, still this will run fine for most implementations for small code. Again, this is a different example. This is a safe code. And again, this is an unsafe code because both are saying MPI receive. Right? So this is unsafe code. Both are waiting for the other process to send data. Okay, so that was standard, what we call standard MPI send. There are others. If you're interested, please read on. I'm not covering any of this in this lecture. Another interesting and important point-to-point communication is using non-blocking communication, whereas I am saying that, okay, I don't want to wait for the receiver to receive my data. I just want to do my other computations. So then I'll use I sends and I receives. But for this, at some point, you have to make sure that, oh, okay, my data has been received. So now my buffer is safe to use. So that's why you will also have to call a MPI wait. This is simply stated. There are some complications and other issues here which you also need to take care of. But to understand simply, this particular code sequence is actually safe because I'm saying, okay, MPI I sent. Both are saying send, and we are not blocked. So this is not non-blocking. So this is a safe code. Okay. Why this is useful is because sometimes the receiver may not be ready to receive, right? It has not reached, it is doing some computation, it's taking time, so the sender wants to do its own computation, so it's often useful. So that was for point-to-point communication. Now we will move forward. Collective communication. So in point-to-point communication, like you saw, there is involvement of
Yeah, participants, please mute yourself. Participants, please mute yourself.
Yeah. May I please request all the participants to mute yourself? so that everyone else can also hear. Right? Okay, so the distinction here is collective communication function should be called by all the processes of that are part of that communicator. If you are using the global communicator as one of the argument, MPI convert as one of the argument, then you will have to call from every process. Okay. So this is some kind of categorization. So there is some synchronization calls like MPI barrier. There are some global communication calls and there are some global reduction calls. And I'll try to cover a glimpse of some of these. Okay, so MPI barrier. So it's possible that because you're doing parallel programming and for some reason you want to wait for every other process to move forward. If you do not wait, maybe maybe you want to make sure that everyone has received the data or everyone has done with this computation so that you can move to the next phase or so on. So sometimes this can be a useful call, although it's recommended not to use this too often, not unless it's very necessary. Simply blocking every other process is not good for performance reasons. Okay. So a very useful call is broadcast. This is a collective call again. What happens in this, one process has the data and it sends the data to all other processes. The same data is replicated on all other processes' memory. So this process that sends the data that has the root, that has the message is called the root process. Okay, and really anybody can be the root process. It depends on the application. Maybe there was some file read. So one process read a file and it now wants to distribute the data. So this is one way to do data. Not exactly distribute the data, but it wants to broadcast that data it read, right? So this is one way. Now again here, like I said, the arguments have to match. Every process that calls MPI broadcast has to have the exact same count, data type, root, communicator. Of course, buffer, the name can be different, but so buffer here is input argument for the root because it has to have that data that it's trying to send, right? And for all the other processes, buffer is actually an output argument. So it receives the data in buffer. Okay. So here is one example. And so here I have the MPI init, com, rank, size. We already know this. And then what I did was here, just for illustration purpose, I have just set color equals rank plus 2. So everyone knows it's rank. And in the broadcast call, so I'll tell you the arguments. So 0 is the root. Okay. 1 is number of data items of MPI int that you want to send. And color is that buffer from where you want to send the data. So here color is an integer and you're saying I want to send one integer from this color buffer. So 0 basically will be broadcasting its rank plus 2 value to every other process, right? So that's why if you print here the old color, right, old color and color, you will see that old color has changed with sorry, not old color, color has changed. Old color is rank plus 2 and color is what every other process received from 0. So 0 is the root. It's sending some value. So think of 0 is sending some value. In this case, 0 is sending 2. Its rank is 2. Its rank is 0 and 0 plus 2. It's sending 2, right? So every other process, if you execute this, every other process, this last value, it will be printed 2. Their old color, which is rank plus 2, that will still be retained, right? So color is output for all other processes other than the root process. Okay. Another interesting call is gather, where one process wants to gather data from every other process. So, for example, I have done some computation, the next process has done some computation and so on. And now I want to collate all the data into one process. So this is a useful call. So you basically get distinct data, but of the same size and type. The send, count, type, these are same as, and also the receive, count and type. So here is another example. Here what we have done is the root is still 0. So here also I've taken 0 process with rank 0 as the root process. And of course I have MPI world, which is the communicator. And then what I'm saying is, so this is the send buffer. Every process, including 0 actually. So every process is going to send this much data from this color buffer to 0, because 0 is the root. And 0 is going to collect all that data into this buffer. So this is actually only relevant at 0. Every other process doesn't get anything in colors. Only the root process, which is 0 in this case, gets data from every other process into this buffer called colors. And here these two arguments say that 0 is expected to receive 1 MPI int from every process. That's all. And so now if you print this, so if you print from any other rank, you will get some garbage. If you print from 0, you will get this color value that every process has sent, and 0 will be printing, so 0 will print 2, and 1, from 1 it will receive 3, and so on. So that's what will be the output of this code. The reverse is scatter. So it's basically 0 has all the data now, and it's going to scatter the data to, it's going to distribute the data to all the processes. It's reverse of what gather does, right? So there are some other collective calls like all gather, where instead of only one process getting the data from all processes, you may have a use case where every process gets the data from all the processes. So you can see the same array is replicated. So in that example, if I go a few slides. So if I was using here all gather call with the correct arguments, then I did not need this if rank equals 0. That colors will be actually not garbage in the other processes also. There are a few reduction functions. So what these functions do are, if you want to reduce an array to a number, so want to compute some statistics, like let's say you want to compute minimum, maximum, or sum of all the array elements present in different processes, then you can use a reduce function. So here I have 3 processes. The first row I'm showing there are 3 different arrays present in 3 processes, and I'm computing the max of those array elements. So it's actually doing a element-wise max of the 3 arrays present at 3 different processes, and that value is present at root. So again, there is a concept of root here for MPI reduce. Only root has that maximum value. Similarly, like for gather, you have all gather. For reduce also you have all reduce. If you want to have the same value at all processes, then you just simply use all reduce. It depends on the use case. What is the difference? The difference is it's intuitively it does feel like that all reduce may take more time than reduce, right? Because in reduce I just have to send the data to one process. But in all reduce, I have to replicate the data in all the processes. I also have to compute max and so on. Although it really depends on the algorithm, and the internal algorithms, which I cannot cover in this lecture, they take 2-3 lectures to cover. So the internal algorithms, it's always not the case that reduce takes less time than all reduce. It depends on a number of other factors as well. But ideally, what you should do is you should use these functions, depending on your use case. Right? Okay, so that is all I had in the slides. And now I can show you some demo codes. I can actually run some codes on our local cluster here, and I can show you some demo. Share the other screen. Okay, so starting with our simple hello world. This is the first simple code I showed you. And how do I compile this? MPI I give a file name and then the code. And then to run, I can use MPI run minus NP, let's say 2 and hello. So it's printing 2 hello world. It has not exited because I have a sleep there. Often I show the students the so you can see that there are 2 processes running. So remember, these are 2, so you can see the IDs, right? The IDs are different, process IDs. The operating system process IDs are different. So there are 2 processes running because I've said, and now it has exited. I had a 30-second sleep, so of course there are no more processes running now. Okay, so if you can really try increasing, I have a host file where I say I specify basically different hosts. Actually, let me just maybe I should just use 4 would be. So now it's running on 2 different systems. It's running 4 processes on this system, which is called CCWS2, because in the host file I have said run 4 processes on CCWS2. Now, if I say run 8 processes, so what's going to happen is you will still see that there are 4 processes running here. And now if you go to the other system and look for hello, you will see that there are 4 other hello world programs that are running, right? So I hope you are able to see, right? So there are 4 different processes on one system, 4 different processes. So these are MPI processes, right? So we have 0 to 7 MPI ranks. Okay. All right. So with that, let's move to and receive code. So here, like I have, so these are the main lines, the send and receive, right? I'm also timing the code, right? So MPI uses a timer MPI W time, which is just a wrapper for some high precision timer of your system that you have used, clock. Okay. So here, like you saw in the example, I have my rank 0 is sending to my rank 1, right? So if I'm rank 0, I will be sending. Else, if I am rank 1, I will be receiving. I have the first two arguments are buff and count, right? And I have MPI int as data type. The source in the MPI receive call, you can see it's 0. That is, I am expected to get from 0, and the receiver in send call is 1. That is, I am going to send to 1. And the tag here I have kept 1. You can really use any integer in the tag. Okay, so let's run this code. Again, the same way we are going to compile. And here I have, so let's try running the two programs, and I have taken two teachers. So I'm saying basically send two, so you can ignore the first argument. So I'm saying basically send two integers, and I can really increase the number of integers. So you can so you can see the time has slightly increased, right? From about 0.1 milliseconds to 1 millisecond, because I've increased the data size by 100 times. Okay. All right. So let's look at some other examples. Maybe gather. Here. So this is the gather function call, right? And that's all. So this is the entire piece of code which is going to gather from any number of processes that you want. You want to gather from 1,000 processes, the same code is going to run. You just have to do MPI CC, MPI run minus NP 1000. It'll still work fine. Right? Okay, so here I have taken input as the number of doubles that we want to send. So I will say, let's say I'm doing a gather from, let's start with small number of processes, and then we'll not timed it here, but I can do a time here as well. Okay, so if you keep on increasing the data size, you can expect that your time taken to gather will increase. If you increase your number of processes, then also increase, right? I have set gather almost, I think, 10 million doubles from 40 processes. So it's going to take a while because this is going to run on 10 hosts, and of course some hosts may be down because this is a shared system. Let me just okay, let's just reduce the number of hosts. Yeah, so it took 8 seconds, right? So this is a shared system. Some hosts may also be down. That may be another reason that code took longer. But of course, I was doing 40 processes. It does take some amount of time in shared cluster. But anyway, so you get the point, right? So increase in data size, your time is increased. Increase in number of processes, your time is going to increase. But of course, it's not very significant, right? It's only, 0.1 3 seconds, 8 seconds, and so on. All right. Just maybe I can show is, so I'm going to show you just a few lines of code. The rest, maybe one of you, so it's almost time to end the lecture. So one of you, maybe you can answer how we can do this. So this is the example to compute parallel sum, right? I showed you a dummy pseudocode kind of in the beginning before we started the programming. So here, I am initializing to some random values, okay? And then I'm doing a local sum. Every process is doing some local sum, right? The final step is missing here. There is a final step where you have to get that local sum from every process, and that is what you have to output. So that is the sum of array or squares, whatever you want to do, right? So here it's sum of squares, sum of just the elements, right? Okay, so with that, I end my lecture here. Before you ask questions about the lecture, if you have any, maybe one of you can answer this part, that how will I compute the global sum? The partial sums are present in all the processes. Okay. Okay, so thank you.
Thank you, Professor Malakar. Yeah, participant.
Can we use MPI reduce for summing all the?
Yes, you can use MPI reduce. That is one way. What maybe another way?
Yes, you can speak. Anybody, we have opened the session, so you can unmute and speak.
Hey, Professor, can we use we can use gather here, right? So because we are
yes, you can use gather, and then after gather, so
yeah,
gather yeah.
Yes, please continue. Please.
Gather itself is not sufficient. After gather.
Mm-hmm. Yeah, since after we have gathered the data, we can just compute the data, maybe accumulate something, or since we
you
basically
will have to do the sum yourself. Right?
Yes.
Yeah. Okay.
Yes, the primary
okay,
task should be to gather the data.
Right. Okay, so good. I think we have understood quite a lot, right? Okay, thanks. So now if anyone has any questions, so organizers, should I like ask whoever has raised hands, or you are going to?
Yeah, we can do it. So actually,
okay.
Participants, all of you have access to unmute yourself. So you can maybe unmute. So Saurabh, do you have a question anymore? If you please raise your hand and we'll sequentialize it so you can unmute and speak. So Saurabh, you have a question?
Yes. First of all, thanks, Professor Preeti, for this introductory lecture. So my question is a bit maybe related to this thing, because it maybe not this talk might be targeted toward the basic level. So, you showed us the list of this top 500 thing, right? Fugaku, Sierra, Summit, and these things. So these supercomputers uses MPI-CH. And let's say
no.
Okay.
They do not use MPI-CH in its pure form. What I mean is, if it's an Intel machine, most likely they are going to use Intel MPI, which is based on MPI-CH. Every MPI implementation is based on MPI-CH, but Intel, if you work on Intel machines, they will be doing some optimization specific to Intel systems. But the base code will be MPI-CH, although we will not call it MPI-CH now, we will only call it Intel MPI. They have their own runtime and everything. Okay, the code may be slightly different because they may be doing some optimizations based on the Intel hardware, maybe. Okay. Again, if you think of, so IBM used to have this massive supercomputers called Blue Gene series of supercomputers. They had, of course, they have IBM MPI, okay, but on so that was, although that was slightly based on MPitch, they had very quite different and lot of improvements based on the interconnect, the topology, and many other very specific improvements they did for all the collectives also, you know. So it really depends on the system. Now in the top supercomputers, these are mostly Intel, Cray. So there's Intel MPI, there is Cray MPI. It's very unlikely that, because these vendors, they do some optimization. So it's very unlikely that one of these open source MPI implementations, which includes MPitch, MVAPitch, OpenMPI, these are generally used in more like, you know, our department clusters if I want to do, or my small, you know, lab cluster if I want to run, because those are proprietary, so we don't have access to those. Okay, so to answer your question, no, they use some proprietary MPI.
Okay. I mean, then again, this the second question arrives is that Cray MPI is there, Intel MPI is there, and there's one open MPI that let's say the source is freely available and people play around, build it. So can you just highlight a bigger difference in terms of big picture between open MPI and?
No, so like I said, much of the, you know, base is out of MPitch. Okay. There is very minor modifications done. I wouldn't say minor actually, because I don't know the source code of Cray MPI. Of course, the runtime is completely different, right? MPitch, so MPitch uses Hydra Program Manager. Cray MPI uses AP Run and many other things. Intel MPI uses its own runtime clubbed with the job scheduling runtime. So the interface is slightly different, but in terms of implementation, right? So implementation wise, it's possible that they have done, I mean, I'm just saying that maybe they have used some Intel specific intrinsics. It's possible, because I do not know the source code. So those are for performance improvement of running an MPI implementation on the Intel system. Okay, but any MPI code that you write, it's going to run 100% on all the systems. I mean, that's why we have the standard, right? The same code actually runs seamlessly on any supercomputer, basically, your cluster or even your laptop. Yeah?
Thank you.
Okay, thanks.
Yeah, Rajesh, can you speak? You have to unmute, Rajesh. Yeah, Asa Lakshmi.
Good afternoon, madam.
Yeah,
I think Rajesh is speaking. Yeah, Rajesh.
Yes, good afternoon, madam.
Yes, please go ahead.
Ma'am, just want to understand about when we are using the MPI. Now, is it when we are using it for a private purpose, like the commercial purpose, the source code should be an open API or closed API, ma'am?
No, so that is absolutely up to you. If you want to develop a, I mean, the source code has nothing got to do with the MPI implementation or anything, right? You are just using the MPI function calls or APIs in your source code. If you want to keep your source code closed source, that's fine. That's your I mean, that's your completely your use case.
No,
Yeah.
ma'am, the reason for asking this question is like, you know, when it comes to the work front or when it comes to the education purpose, when we try to get the integration in our work portfolio, most of them ask like, do your tool or platform as an open API or closed API, so that the integration is difficult and technicality have more complications. So that's the reason I asked this question, ma'am, just for the knowledge to understand from your end.
See, so if you're developing an MPI application, let's say for your use case, your scientific use case, and your organization does not want it to be, you know, publicly available, that's completely fine. There are groups which keep their source code, do not make their source code publicly available. There are many groups who make their source codes, of course, publicly available, mostly in academicians. you will find the source code is publicly hosted somewhere. But there is nothing from MPI point of view that you can or cannot do. It's completely your use case.
Yes, ma'am. Well, thank you, ma'am. Thank you for the information. It was a very wonderful session, ma'am, from your end.
Thanks.
Any other question? Any participant? You can also mail us the question in the email address you have provided. We will forward all the questions to the speaker. Let us then thank Professor Malakar for the excellent talk, and I hope that it will be very useful to all of you as we go ahead with applying such programming practices in enabling your programs with such libraries. It will be great help to all of us actually, and we hope to hear more from Professor Malakar in our future workshops, which will be more detailed on these topics, more deep diving into the individual aspects of the applications. And thank you again. Thank you, Professor Malakar, for the excellent talk. And